Hello everyone, and welcome back to another Labs stream. I'm the Mad Lad, and today we're going to be taking another look at the single board computer components on the the homing or guided missile robotics project. Uh, so, as you can see here, I got a little uh, video displaying in the browser, and this is coming from a small single board computer. Uh, for reference, that's an UpCore with one of the Aeon, that's the manufacturer of upboards, produced cameras behind me. They make a camera that comes in a little nice metal enclosure. So I think that's one of the reasons I like it. It has, the metal enclosure plus a mounting bracket, so it's easy to mount on things. But, we finished the last stream with me doing a little, teaser as to what the HMI, or the human machine interface, for the guided missile or homing missile robot is going to look like. So, you have this uh, video feed displayed in a browser, and then you can designate some sort of a object that you want to track on the screen. So I'm going to pick up this measuring tape. Well, can't really see the color here very well because there is a bright light right over here. All the colors, you can't really tell them apart. You probably need something transparent to be able to track them. Where here's a roll of tape, so maybe if I give this as the object that we track, we'll get pretty good performance. So here is the tracked object. I can move it around. I don't want to move it over here in front of the laptop monitor, because there's now going to be a lot of contrast, and the tracking will probably fail. But for the most part, you know the the object can move pretty fast in the frame and still be trackable. Anyway, uh, as you can see here, there's a couple of things happening. We're grabbing a frame from a camera. It then goes through some computer vision logic to handle the object tracking if an object tracker is set. And there is obviously the browser or the UI component, which displays the image and provides an interface to be able to set the tracking for the computer vision part of the whole single board computer systems. So what I wanted to do today was to actually start prototyping, start breaking this prototype app, which is a monolith. It's a single app that does three things. It has, it handles the image capture from the camera. It handles the computer vision object tracking part, and it handles the website as well. Instead, I want to break it down into three components, and I want those three components to be built using ROS2, which is Robot Operating System 2, if you're not familiar. And the reason I want to use ROS is because ultimately this is a, a robotics project. Yeah, it's called guided or homing missile or whatever. But at the end of the day, it's a robot. It looks at the world, it tries to identify something in the world, and it tries to perform an action using what it sees, which is very much, like a lot of what industrial robotics do. So, at the end of the day, it's a robotics project, uh, and ROS2 will provide, it should provide plenty enough performance for something like this. It's not like, if you were actually making a homing missile, you probably wouldn't use ROS2 or ROS in general. You would probably have your nice monolith, which is super tuned for performance or whatever. But, you know, we're not making weapons here. It's a robot that's meant to pop a balloon. So ROS2 is going to be plenty good. Some constraints because I expect there to be a fair amount of delay or latency in my controls or other guidance. Uh, the controls I would expect to be pretty fast because they're going to be running on a microcontroller specifically on a TZ4. So I'll be able to have those controls run nice and fast. The bottleneck there would be the sampling frequency on the IMU as far as controls go. Other than that, you know, the next bottleneck is really the guidance system, and I would expect, we've been when we look at this video, it's actually, I don't know exactly what the FPS is, but maybe we're getting like 10 to 15 frames per second here. Maybe I'm being optimistic. So let's say we're getting 10 frames per second, which means our guidance system updates, every 100 milliseconds. There's going to be some delays between, when you capture the frame and when you finish processing it. So you're going to have a delay in you seeing something and you being able to respond to it. And that goes back to this isn't a real missile. This is just a robot plane that's popping a balloon. So I can make the plane nice and slow. I can have an airframe with big wings and a fairly lightweight frame as well. This way it can just glide along slowly towards the target. Anyway, enough rambling for now. Getting back to the project, so let me close this and get back to our little system, I guess, summary here. So what we've seen in that browser are, obviously we had some sort of camera pulling happening, we had some web hosting and UI, and we had a computer vision node that we saw there as well because we had tracking. We didn't see any guidance because for guidance we actually need to know what the orientation of the plane is. This way, if the camera is tilted, you need to be able to say, oh, this pixel really corresponds to this coordinate relative to, let's say the front of the plane. And then finally you have the flight controller comms node, which is once again, with the whole, these two components really depend on each other. You can't, well, you can build the guidance node, but it's not going to work until you have the flight controller comms node. So today we want to get started on these three nodes, and I've already did a little bit of prototyping. So since last stream, I put together, I'm running all of this on my UpCore board, and I have a couple of Ansible playbooks. And just to those not familiar, Ansible is a uh, kind of a configuration language where it's a configuration deployment language that allows you to uh, make configuration changes to a remote system. That system can be a lot of things. It can be, it can be a VM. It can be pretty much any physical computer or virtual computer. It can be a network switch. Pretty much as long as you can SSH into it, you can configure that device. And by configure, I mean you can install some packages, run commands. You can do whatever you want, because ultimately, if you can SSH onto something and run a shell command, then you can pretty much do whatever you want on the system. So on the little box uh, that was streaming the video before, we have a couple of, or I've set up that box to do a couple of things. One is I've set up that box to allow me to run my code without really containerizing it, and I also set it up so that I can have Docker on there as well, since that's how I plan to deploy things. And I mentioned it before, but why use Docker? You want to use Docker because you can have nice, consistent environments from one execution to another. A lot of times when people develop, they unintentionally create snowflake environments that they develop in, and then someone else might try to replicate the environment. That someone else could be the same person that did it the first time, and they go to run their code and it doesn't work, and then it's not obvious as to why it's not working. So containers are kind of like VMs in the sense that they allow you to have somewhat isolated environments, but the the difference is that it's not fully isolated in the same way that a VM is. It's all actually still running on the same machine, whether it's a virtual machine or a physical machine. But you do have some isolation between the different containers. Anyway, this video isn't really to talk about containers, but I just wanted to mention why you might want to develop using containers, and that's to have consistent environments for your code. That's one of the reasons. Anyway, since last video or last stream, I've been coming up with a couple of test Docker test Docker packages to do a couple of simple examples. There's a pub sub example in here, and this repo can be found on GitHub. I think it's github.com/madladlabs, capital M, capital L, capital L in MadLad Labs. And the repo is called cv.guidance, I think. Let me check. Git bash. Yeah, it's cv.guidance. And the code that you're seeing here is on a feature slash flask-web-viewer branch. Otherwise, if you go into master, odds are it's probably going to be empty in there. And then even if you go on the develop branch, that's going to be probably empty too. Anyway, so as I said, we have a couple of packages here that I've been playing around with. PubSub, I just wanted to get stuff working in a Docker example. So I have two nodes in here. One is a publisher node, and what the publisher does is every half a second it fires off this callback, this timer callback function, and in this function we go ahead and we publish a message that says message number blah blah blah, and we log that we've published this message. And we keep incrementing the counter for the message numbers. And in the subscriber, we just simply receive that message. So we start listening on this my topic, which is the same topic from the publisher node, and we execute this listener callback function. And in this function, we just take the message and we log the data from the message. So I'm not gonna run this example, but just because it's so trivial, the main part here was really to put things in a Docker container that runs consistently, and it works. So you should be able. There's a README right here. If you just clone the repo, switch to this branch, run these commands, then run this, it should work. And you can use these Docker files for reference as to how to build your packages in a Docker container. The ROS page on Docker Hub actually has a much more robust example of building a package, but because this stream isn't really about getting hardcore with Docker and ROS, like to get at the pro level, this project is really here to educate like on bare basics, just to get you going. And since we want to educate, I'm just going to go through what's happening in these Docker files. So we copy our code, which is in this PubSub example, or sorry, it's in here actually, PubSub example directory. We copy that into our R container, into root / ROS2 packages / PubSub example directory. Then we change our work directory to ROS2 packages. Then we run this dot /opt ros foxy setup.sh that will set up our shell to have the correct environment to interact with ROS components, including stuff like calcon. And so we use this setup.sh file, and then immediately we run calcon build which will build the package. And the reason, excuse me, got something caught in my throat. The reason why, we do setup.sh and calcon build is that whenever you use the run uh, statement in a Docker file, all of these run statements, they're isolated from from each other. It's basically like opening up a new terminal to your Docker container and then running a command. And this setup.sh isn't part of your bash rc file. So this setup, the setup logic isn't going to be in that instance of the execution, and then calcon build wouldn't work. So that's why, whenever you want to run a a calcon or whenever you want to do ROS related stuff in a run statement, you want to first use the setup.sh and then immediately follow that by whatever you actually want to run. Finally, we want to update our ROS entry point to actually use the setup bash script that comes out as part of the build process of our ROS packages. And the ROS entry point shell is the entry point in the Docker container that gets executed before we go to actually run something in the container. So all of this stuff right here, copy, work dir, run, this is part of the build. And then this command statement is what we actually want to run when the container starts. So, we copied our files over, we changed our work directory, we build our code, we updated our entry point script for the container, which sets up our ROS environment in the terminal or in the in the shell instance that the container runs in, or that the container runs with. And then finally, once the container starts, we're going to go ahead and run the command ros2 run pub sub example, because that's the name of our package, and we're going to do subscriber node. So that was a a brief overview of the minimum requirements to build a pub sub, or pub sub, which is kind of like the hello world of ROS2 using containers. And if you look at the publisher Docker file and the subscriber, they're pretty much the same thing, except that the subscriber has subscriber node in here, and the publisher has publisher node. Moving on to a more interesting example, we have the image pub sub example here. And here, I've been playing around. It's still a pub sub kind of hello world example. However, here the message that we transmit is an image, as the name of the package suggests, and we actually start using a browser to display that. Since I'm running in a headless environment on the single board computer, I don't really have any way to display images except through a web browser. Plus, the web browser is the intended interface for the guided missile or the homing missile robot. So if we look at our publisher node, we have a couple more things happening here. We we add some more things here. We add, instead of using the string type message, we now use an image type message. We added a CV bridge class from CV bridge module, and that allows us to it's a utility kind of class that converts your images from CV2 or OpenCV to the ROS2 message format. If we actually look at the publisher node here, the changes are that now we're using image as the message type for creating the publisher. We added a parameter here called image path, and that's the path to the image that we want to load from the system and start transmitting. I keep using the word that sucks. Instead, you're supposed to just shut your mouth and be quiet. So that's what I'll try to do from now. We grab the parameter from our environment, or from the ROS environment. We assign that to the image path variable, and then there is a potential that when we started we didn't have the image path parameter set to anything, so we don't want to move on with the rest of the code unless we have it. So the best thing is to just continuously spit out messages saying, oh, you didn't set image path, because maybe you're running in some other environment where you can use the ROS command line interface to supply that parameter later on. Finally, we log the image path that we want. We read in the image from the system. We set up our timer for the publishing, and we fire off our timer callback, where the timer will fire off the timer callback function. And we also initialize a CV bridge, an instance of the CV bridge class. And in the timer callback, whenever that executes, we log that we're publishing an image, and we actually publish the image, and we use the CV bridge class to convert our CV2 image to an image message. And the main function here is the same as before. And the subscriber, it gets a little bit more complex. We introduce a couple of things in here. So similar to the publisher, we have a CV bridge, we have an image type message, we have other ROS stuff. We add a couple of classes and a function from the Flask module. We also import threading and time, and that's to create some there we go with the again. The threading module is used to have a shared memory location that holds the image, and for us to have a lock to make sure that we're not reading the image at the same time as is being written to. Did I say that right? I think I did. Well, just again, we want to make sure that we're not accessing the data at the image location in the memory at the same time as we are writing to it. So we have our subscriber node. It creates a subscription listening to my topic and expects an image. And whenever a message comes in, it's going to fire off the listener callback. We create our CV bridge so we can convert the image message to a CV2 image. And we also initialize the stored image within the subscriber node, and we also create a lock. We, in our listener callback, we log that we received an image, and we also take out the lock, and we assign the image that we received in the message to the buffered image that's stored within the node. Finally, we have a get image function on this node, and that allows us to read the image in a thread safe way because we're using the lock. This is once again a threaded application. So we have a function that initializes the thread that's running the web app. So we create a Flask app. We serve an index.html view whenever you go to the root of the website. We have a generate function which gets the image from the subscriber node, and then if we do have an image, we will return it as a frame for our video feed. This time.sleep here is to give up a little bit of time on the it's to free up some execution time so other threads can run, since this is a threaded application, and the web app itself is also threaded on top of this top level thread which runs the application as a whole. The requests that are coming in are also handled in a threaded manner, so you want to give up any time that you have available to other threads which might actually be doing stuff, instead of constantly polling, hey, do I have an image? Do I have an image? Oh, I need to send it to the client. Since we are expecting our image web video feed to be 10, 15 frames a second, this is way fast enough to make sure that our video feed is more or less real time anyway. And here we have a video feed route, and here we just use the generate function from up here to serve up basically a video. And we, at the end of this web thread function, we run our web app, we bind it to anything, and we host it on port 8080, and we set it up as a threaded Flask app. In our main function, unlike some of the other ROS2 nodes that we've seen here so far, we don't just create a subscriber and start spinning it. Instead, we first create the subscriber, then we create a thread that runs our web thread function, and we pass it our subscriber object. We set the thread as daemon. We start the thread, and then we start spinning our subscriber node. This spin function is a blocking function, so the app basically isn't going to exit until the subscriber decides to exit or crashes, or we send it a termination signal. So that's the app here, and I'm gonna run this locally for now. Let's see if I have it over here. I don't need, let's see, I think I've already tested it before. Yeah, I'm going to run it locally, not on the little box, just because I haven't pulled down the latest. Or actually, you know what, let's see if we can get it working on the box. So let me kill the current web app that we have running on there. Let's cd to the root level. Let's check out the current branch that we are on. And let's pull down the changes. Okay, so we now have a lot more things, but we should be able to run the examples, this image pops up example, using the information from the README here. So package is created using that. We don't need that, but we need to know how to build it. So I am going to navigate to the package, which is located in ROS 2 image pub sub example. Let me ls here. Yep. So now I should be able to copy paste these commands. Ooh, this might take a while. 120 meg downloads. Probably not going to be too long, but typically the first image build is going to take a while. The second, or it's not an image, it's a container. The first container is going to take a while to build. The second container shouldn't take too long to build because it's going to reuse a lot of the cached parts of the first build. So just a small note on writing Docker files. Whenever you have parts where you might be installing different packages in a container, you want to put those up first. And if you have multiple Docker files that start from the same base image, you want to keep your additional package installations the same across different package files, and then in the end is where you actually want to go ahead and copy and build your code into the image. And the reason why is whenever Docker builds up an extra part from your Docker file, for example this run statement, it will cache the result, and then when it runs this, it will cache the result. So for example, we have this publisher node here, and we install Pt.3 dev and Pt.3 pip in here, and then we install ffmpeg libsm6 libx6, there's going to be a cached image with, Rust Foxy with Python 3 dev and Python 3 pip installed, and there's going to be another cached image with ffmpeg and other packages listed here installed. This way, when the Docker file for the subscriber is being built, it sees, oh, I need to start from this image. Okay, I have this image. And then it says, okay, I need to now have this run statement applied to my base image. And then it looks through it in its cache and it sees, oh, I already have this. Or I already have ROS with this run statement applied to it in the cached image, so I don't need to rerun this step. And then it will move down the list and it will also see, oh, I already have this cached as well. This way, the long-running steps that are included in your image builds or container builds, they're all similar, or they're all run the same way across multiple container Docker files. This way they get to share the build times, where you only need to build these things once, not every single time you run the build. Anyway, going over these Docker files, unlike the ones from before, we install a bunch of stuff. We install some more things for Python 3. This is for CV, or their OpenCV. This is a package for the CV bridge module. We install some pip packages for OpenCV, NumPy, and imutils. I think we actually might not be using imutils in this package, but I often include it anyway, just in case I might use it. And then finally, we have the similar kind of code from before, where we copy our code, we change our work directory, we build. There's a little bit of difference here again, because we copy the images for the published image that we want to display, or that we want to communicate to any other nodes that might be listening. And finally, our ROS run command is slightly different, because we don't just give it a package name and a node name. We also say that we want to pass in a parameter for our node, which is the image path, and it's set to /images/docs.jpg. And in the subscriber, we install a bunch of stuff. And on top of that stuff, which is similar to our publisher Docker file, we also install Flask, since we have the Flask app hosted in this node. We do our copy and build. We also copy our HTML templates for the websites. We set an environment variable, because that's how the website knows, in our case, that's how the website knows where to look for the view templates for that index.html file. And finally, we have our ROS entry point update, and we expose port 8080 so that we can host the website. So let's see where our build is. This is a pretty long stream so far. We're way past 40 minutes right now, and I'm trying to wrap it up. I want to finish on this demo, and hopefully this will finish soon. So this is, let's see where it's at right now. I think I see OpenCV stuff, but it doesn't look like pip, so I'm guessing this is actually this step right here where we install the CV bridge, because that installs many OpenCV packages in the container. Okay, and yeah, and now we're running the pip3 install. This is going to take a minute or two. Unfortunately, right now, uh, nobody's watching the stream. Of course, I'm streaming at ridiculous hours of the day, or night, rather. Maybe, yeah. If someone would be watching, it might be someone from the West Coast. But okay, we finished our container build for the publisher. Now we're going to do the container build for the subscriber. So let me get that going. So this is going to be way faster since it already used the cached images that already have the modules installed that are shared with the subscriber node. And as you can see here, it's already building our code, which shouldn't take any time at all. And yeah, there we go. We have our container build. So we're gonna first start by running the publisher node. Make sure it starts and runs successfully. Okay, it's publishing the images. Oops. Can't exit out of it, so I'll just create a new terminal here, and I'm going to SSH once again. I am going to log in. And I'm going to run the subscriber node as well. So there we go. It's hosting the website. It's receiving images. And let me fire up a web browser. And let me navigate to the page here. And there you go. We are listening, or we navigated to the web page. It's got the ROS2 image stream, and technically this is actually a video feed. However, it's all the same image, so we don't see any changes. Anyway, I think we're gonna stop it right now because we're almost coming up on 15 minutes in the stream here. So thank you for watching, and I'll see you next time.